So this is the 11th session on Newton's laws of motion. This is also in continuation of the 10th video. Okay. So in this video also I'll take up a numerical problems on Newton's laws of motion. Okay. So I'll take up 2 more questions. Okay, fine. So I write down the question first. Question 1 is this. A thin uniform rod of length L equal to 30 centimeter and mass equal to 3 kg is resting over a smooth horizontal surface over which it is free to move. It is free to move as shown. This is the smooth horizontal surface, side view. This is a thin uniform rod of length 30 centimeter L and is placed over a smooth horizontal surface. Mass of the rod is 3 kg. Also, constant forces F1 and F2 act on the rod as shown. F1 and F2 are constant horizontal forces acting on the rod. F1 constant force, suppose it has a magnitude of say 16 Newton, and F2 is also a constant force in leftward direction, that is say 1 Newton. Okay, so 2 things we have to find. First, the acceleration of rod with respect to ground. Acceleration of rod with respect to ground, okay, in magnitude and direction both. And second thing we have to find that find the interaction force on the portion of rod at a distance of 10 centimeter from its left end. Due to the remaining portion. Due to the remaining position. Okay, these 2 things we have to find out. So this is the thing. Okay, so now we solve this question. Solution. First we solve the part 1 of this question, acceleration. For this what we do, we draw the free body of this rod with respect to ground. Okay, so I'll draw the free body diagram of the rod with respect to ground inertial frame, as I've been stating in previous videos. So this is the mass, weight 3g. Mass of the rod is 3 kg. G is acceleration due to gravity. The ground exerts a normal force on the rod n in upward direction. Rightward force F1 acts on it, whose magnitude is constant 15 Newton. And constant force F2 acts on it in leftward direction, whose magnitude is 1 Newton. Okay. Now from this it is seen that the net vertical force on the rod is 0. N and 3g cancel each other. And net horizontal force on the rod is 15. This is 16. Sorry, 16 Newton. Okay. Net horizontal force on the rod is F1 minus F2 from parallelogram law of vector addition. That becomes 16 minus 1. That is equal to 15 Newton. So net force on the rod is equal to 16 minus 1 equal to 15 Newton. That is equals to mass times acceleration. Mass of rod is 3 kg. A is the acceleration of the rod. Okay. So from this we get A is equal to 5 meter per second square is therefore the required answer. Okay, this is answer to part 1 of the question. Okay, fine. So in this I have applied Newton's second law to the rod with respect to ground in rightward direction. So F dash becomes 16 Newton, F double dash becomes 1 Newton. So net force becomes 16 minus 1, that is equal to 15, that is equal to 3 times A. So A becomes 5 meter per second square. First answer I have obtained. Okay, I love this one. Okay, now what we have to do, we have to solve part 2 of this question. We have to solve part 2 of this question. Okay, so for that, to solve the part 2 of the question, I draw the diagram here again. So solve the part 2 of the question. So this is the side view of the rod. Okay, this is given to be 30 centimeter. Here 60 Newton force is acting rightward and constant 1 Newton leftward force is acting on it. This is the section whose distance from left hand is 3 centimeter, 10 centimeter. Now we have been asked to find the force on this portion of rod due to the portion of rod to the right of this. That is, we have to find the net force on the rod in this much portion of rod due to remaining portion of the rod. Force on this portion due to this portion, we have to find out. Okay. So let us assume that this portion of rod of length 20 centimeter exerts, say, rightward force of F on the portion of rod to the left of this 10 centimeter rod length. Okay. Now what I do, I draw the free body diagram of this portion of rod of length 10 centimeter. Of this I draw the free body diagram. So first, mass of this 10 centimeter part of the rod. The rod is given to be uniform. So 30 centimeter rod length has a mass of, say, 3 kg. So 10 centimeter part of rod will have a mass of, say, 3 kg by 1/3, 1 kg, because the rod is given to be of uniform density. So here I get 1 g. Okay. Here I get a normal force N1. Okay. Here 1 Newton leftward force is acting on it. And this portion of rod exerts a force F on this portion of rod, rightward force F. Now apply Newton's second law to this segment of the rod in this direction. N1 and 1g have no component in that direction, only these two forces are there. So F dash becomes F, F double dash becomes 1. That is equals to mass of the length of the rod mass of rod whose length is 10 centimeter. As I have stated, this rod is uniform. So 30 centimeter rod length has a mass of 3 kg. So 10 centimeter rod length will have a mass of 1 kg. 1 into A. But A we have found it is 5 meter per second square. 1 into 5 becomes 5. So F becomes 6 Newton. Okay. This is the required value of F. Okay. So it's the answer to part 2 of the question. Fine. Alright. Now I love this one. Alright. Fine. Now I take up one more question. Okay. Now I take up another question of this in this video. Okay. I'll write down the question first. A small block of mass m is thrown vertically from ground in upward direction with initial speed u. With initial speed u. Okay. Apart from the weight of the block, a resistive force Fr equal to m lambda v square acts on it, where lambda is a positive constant. Lambda is a positive constant, okay, and v is the instantaneous speed of the block. V is the instantaneous speed of the block. V is the instantaneous speed of the block, and the resistance force implies that the force on the block is opposite to its motion direction, okay. This means that since the block is moving upward, the resistance force on the block will act in downward direction. That's why it's called resistance force, okay. The question is this: find the maximum speed, maximum height attained by the block. Find the maximum height attained by the block from the ground. From the horizontal ground. Okay. In terms of the given quantities. Lambda, G, okay, and U. Okay, fine. So now I solve this question. So again, what we have to do? We draw the free body of the block at some arbitrary instant during its upward journey. Okay. So suppose the block is projected from ground with initial speed u. Okay. Now as it moves up at some instant, suppose the block is projected from here at time 0 with initial vertical speed u. Now as it moves up, two forces act on it. Force mg in downward direction, weight, and the resistive force which acts on the block opposite to its motion direction, that also is in downward direction. So at some instant t, the block has come here. At this instant, its speed has decreased from u to v. At this instant, I draw the free body diagram of the block with respect to ground frame. Only real forces will act on it. mg and a resistance force m lambda v square. Okay, m lambda v square mg. These are the two forces acting on it, real forces. Okay. Now, suppose the block is at this instant t, it is at a height y above the ground. Okay. Now mg is in downward direction, m lambda v square is also in downward direction, and the block is moving upward. So motion direction is opposite to the net force on the block. So as it moves up, its speed will go on decreasing. So when it attains a maximum height at this instant, it is instantaneously at rest. And suppose its height from the ground is h at that instant, which you have to find out. This h you have to determine. Okay, fine, all right. So at this instant t, I apply Newton's second law to the block in upward direction. Okay. At this instant t, I apply Newton's second law to the block in upward direction. Okay. So what I write? M dv by dt is equal to net force on the block in upward direction. That is equals to f dash minus f double dash. What is f dash? F dash is the sum of components of those forces on block which make acute angle with the upward direction. There is no such force which makes an angle of acute angle with the upward direction. So this term goes away. What is f double dash? F double dash is the sum of the magnitudes of components of those forces on the block which make obtuse angle with the upward direction. Now these two forces mg and m lambda v square both are in downward direction. They make 180-degree angle with the upward direction. That is obtuse angle. So f double dash simply becomes mg plus m lambda v square. So this I'll write as 0 minus mg plus m lambda into v square. So this is the required equation. Okay. Now when asked to find the maximum height attained by the block, so what we do? We apply chain rule. So I write it this way: m into dv by dy into dy by dt. This is how I write chain rule. Okay. This becomes minus m goes common plus lambda v square. Okay. Now m and n cancel out. Okay. Now if we know from kinematical theory that dy by dt is v, instantaneous velocity of the block. So this is replaced by v. So we get v dv by dy equal to minus of g plus lambda v square. Okay, fine. So this is the equation in v, differential equation with y as the independent variable and v as the dependent variable. So if you solve this differential equation, we get the maximum height h attained by the block. Fine, all right. So this side of it, okay, fine. So now I solve this differential equation. I try to rewrite it here. So it becomes v dv by dy equal to minus of g plus lambda v square. So this implies v dv by g plus lambda v square equal to minus of what? Dy. Okay, fine. Now what I do, I multiply this equation by 2 on both sides. So I get 2v dv by g plus lambda v square equal to minus of 2 dy. Alright. Now what I do, I integrate this equation on both sides. So this becomes 2v dv by g by lambda plus v square. I take lambda common. Lambda I have taken common outside, okay. Lambda is constant. So lambda comes outside the integral, okay. This becomes minus 2 integral dy. Now what is going to be the limit of y? Initially the block was at ground. The y is being measured from the ground itself. So initially y was 0. When y was 0, the initial v was just equal to u. And when the y becomes h, maximum height, its speed v becomes 0 instantaneously. Alright. So this we get 1 by lambda is outside. Now this when integrated and inserting limits, what do we get? Yeah, sorry, here upper limit will be 0, sorry. At this maximum height v is 0, it is at rest instantaneously. So this becomes 1 by lambda log of g by lambda plus what? 0 square minus log of g by lambda plus u square, okay. This becomes minus of 2h, okay. Dy, integral dy 0 to h becomes h. So we get what? We get 1 by lambda is common. So log a minus log a by b. So this becomes 1 by lambda log of g by lambda plus u square, okay. This becomes minus of 2h. From this we can get the value of h. See, minus 2 comes here, so it becomes minus 1 by 2 lambda log of, this becomes g plus lambda times u square, okay. Fine, alright. So I have this one now, fine. So this becomes h equal to 1 by 2 lambda, minus sign if we replace, then this gets inverted. This log is basic, natural log, okay. This becomes g plus lambda u square by g. Alright, fine. So this is the maximum height attained by the block in course of its motion. So this is equal to 1 by 2 lambda log of base 1 plus lambda u square by g. This is therefore the required answer. Fine, alright. I hope it is clear, alright, fine. So in this session also I have taken up Newton's law problem, okay, fine. Now in 12th video what I'll do, I'll take up questions on this pseudo force theory, okay. First I'll discuss the detailed theory of pseudo forces involving rotating frames, okay. And then I'll take the special case of pseudo forces for a translating non-inertial reference frame, okay. And then I'll discuss the concept of combined equation of motion, okay. And then I'll take up different types of numericals on that subtopic, okay. So this I close it here, fine, alright.